So good evening and welcome to today's live session for the course Element of Mechanical Vibration NOC25-ae17. We are into the week 4 live session for this course and we have already completed 3 live sessions up till now. So this week was mostly concerned about impact if we subject our system to any kind of impact and what or how should we take out the response if that impact is not actually applied at exactly t is equals to 0, but that it is applied after some time after we start observing the system. And then the discussion was about forced system, a spring mass dashpot system or a spring mass system, and it was subjected to harmonically excited force. With harmonically excited force, we mean something of the form F sine omega t or F cos omega t. However, we will be studying about what other kinds of forces are going to cause in the system, but here we are mostly concerned about harmonically excited systems. Okay, so we'll be starting with the first questions. Okay, so see. So I've taken the questions in such a way so that it will be helpful for you to solve the assignment problems. Okay, so coming on to question number 1, which says that, yeah, in the vibration testing of a structure, an impact hammer with a load cell to measure the impact force is used to cause excitation. Okay, there is no point of as shown in figure. Assuming M is equals to 5 kg, K is equals to 2000, C is equals to 10, and F is equals to 20 Newton second, find the response of the system. Okay, so firstly, how is the excitation? Excitation is somewhat like this is the time, this is the force, and the excitation happens at t is equals to 0. This is our excitation, which is in the form of impact loading, wherein we have this value as 20 Newton second. Okay. So basically, this is a force which is applied to the system for a small amount of time, a high amount of force for a small amount of time. So the total effect is taken by taking the area under the curve, which is F, the total force, let us say F dash, into time, and the total value is given as 20 Newton seconds. Okay. Now, we have to find the response of the system. Okay. So first thing is that we are going to We are going to model our system as a simple spring mass system, spring mass dashboard kind of a system. And then we apply a impact loading on it, right? And we have to find out that what is going to be the solution for the system when such kind of a forcing is applied. So this is the loading, impact loading, right? And then we already have the parameter values, which are mass, 5 kg, spring stiffness as 2000 Newton per meter, damping constant as 10 Newton second per meter, and then F we have as 20 Newton second. Okay. So for a spring mass system, we knew what is going to be the solution, right? We knew what was going to be the solution. We already derived it. Okay. Considering that there is no forcing. So for a spring mass system of the form mx double dot plus cx dot plus kx is equals to 0, we had the solution x of t written as e to the power minus eta omega n t into x naught cos of omega dt plus x naught dot eta omega n x naught divided by omega d into sine of omega d t. Now here we don't have m, c or k because we try to transform it into a form where we use eta and omega n. So if you remember, we had the equation as omega n is equals to under root of k by m, right? Where we already have k and m, so we can find its value as under root of 2000 by 5, which is 20 radians per second. Okay, then we have to find out eta, which is C by Cc, and Cc is the critical damping constant, which is written as twice of under root mk. Sorry. So when we put these values, we get this is 10,000, which is 5 by 100, 0.05. So this is our eta, which is the damping ratio. And the last thing that we have to find out is omega d, which is the damped natural frequency. This is the damping ratio. This is the damped natural frequency. This is the natural frequency. Damped natural frequency, which is given as omega n into under root of 1 minus eta square, which is nothing but 20 into under root of 1 minus 0.05 square. And this will give us the value approximately 19.975 radian per second. Okay. So now since we have all these values, we can write this equation on the basis of the initial condition. So you see over here, it is written that it is the system that we are assuming it is for the impact testing, right? So for the impact testing, our sample is in a steady state, like it is at a zero state, where its velocity is zero and its displacement is zero. Okay. So initial condition is x naught is equals to zero, x naught dot is equals to 0. Minded this I'm telling when we have the system in such a way such that we don't consider the impact as of now. As of now. Okay. But now we are actually giving an impact at t is equals to 0, which is going to give a velocity to the system. So we assume that this impact is for a very small time, and hence we can say that the initial condition, the initial position before the impact and immediately after the impact is exactly the same. So we are going to take x naught is equals to 0, but we are going to take x naught dot is not equal to 0. And this value we are going to get from where? We are going to get this from the effect of forcing, right? So when you see for a system, if we talk about force, which is equals to mass into acceleration. So if you remember, there was a definition which says that mass into acceleration can be termed as rate of change of momentum. Okay, where momentum is what? M into V. Using that, we can actually relate force, the impulse force, and the velocity. So you are going to get that this impulse force F can be written as what? mv. This impulse can be written as mv. Okay. So if I have this and F is applied at the initial time, then we can say that after the impulse is applied, what happens? Whatever the velocity that my system is having is actually acting as the initial velocity. So we can write x naught dot as v, which is equals to nothing but f by m, which is equals to f by m. Okay, here f is initial impulse. Okay, I hope this is clear. So now we have the initial condition as x naught is equals to 0 and x naught dot as f by m. Okay, so now if I want to find out the solution, if you look over here, this e to the power minus eta omega nt is going to remain. Then we have x naught cos omega dt. X naught is what? X naught is 0. X naught is 0. So this will go to 0. Here also x naught will go to 0. Right? So what remains? What is actually left? X naught dot, which for which we already have a value. So if we use that value and write the solution, what is it going to be? The solution is going to be x of t is equals to e to the power minus eta omega n t into f by m omega d sine of omega d into t time. This is going to be the solution for an impact which is applied at a time t is equals to 0. I hope this is clear. Okay. Now I can further write this as x of t is equals to f into g of t into g of t, where g of t is nothing but e to the power minus eta omega nt into sine of omega tt divided by m omega d. Okay. So this g, which is a function of time, is actually changing with respect to time, but the force F, which is the impulse, it is a constant value and it may change from system to system. So if I have now different kind of a system for which I have the initial impulse value and I have the system parameters, I can simply find out the equation of motion by this form. Okay, I hope this is clear. So now for the given values, if I want to find out the solution, F we already know is 20. So we write x of t as 20 by m, which is 5 into 19.975 e to the power minus 0.05 into omega n which is 20 t sine of 19.975 t. So if we put out all the values, the final form is written as 0.2005 e to the power minus t sine of 19.975 t. This is the final solution, considering the initial condition and every single thing about the system. I have already done the calculation, I have written it, so you can verify all the numerical values and the calculations. So this is going to be the final value. So now if you have any question which says that, okay, this is the impulse which is applied at the initial time t is equals to 0 for some time, and these are the system, if you want to model it as a single degree of freedom system with a spring, mass and dashpot, you are going to simply put the values in this equation and you are going to get the solution. Now if I have this equation x of t in terms of time, for any time t greater than 0, I can find out the solution by putting the value of t in this equation. Okay, I hope it is clear. Coming on to question number 2. So in many cases, providing only one impact to the structure using an impact hammer is difficult. Sometimes the second impact takes place after the first, as shown in figure, and the applied force F of t can be expressed with the Dirac's delta function, where t indicates the time between the two impacts of the magnitude. For a structure with M, K, and C, find the response of the structure. Okay, so we have the behavior something like this. I'll again redraw it. First impact is at time t is equals to 0. Second impact is at time t is equals to tau. Okay, and then we have the value of F1 and F2. Okay, so now if this is the case, how are we going to find the solution? Like in the previous question, we were having only one impact, which was applied at the initial state at time t is equals to 0, which was fine for us. But this time we have two impacts, and the time span between these two impacts is tau. Okay, so how do we find a analytical solution for this? So firstly, we are supposed to write this uh, impulse function in terms of time. So we can write it as f1 of delta t plus f2 of delta t minus tau, where delta is nothing but the Dirac's delta function, right? We can write the impulse force that is applied to the system like this. Now, if we take f1 as 15 Newton and f2 as 10 Newton, and when we try to find out the solution. Now, first thing is that for the first case, if we consider what is going to be the solution for the first case, if we consider only F1, okay, and let us say that we want to find the solution before the second impulse is applied. So we already know the solution, which was of the form x1 of t, which was of the form f by m omega d e to the power minus eta omega n t sine of omega d t, right? When we put the values, we get 15 by 5, 19.975, because here also if you'll see the values are same. So if we find out omega n, it is same as 20 radians per second, eta as 0.05, and omega d as 19.975 radians per second, because the parameter values are same as that of the previous questions. Okay, e to the power minus 0.05 into 20t sine of 19.975 t. So now when we calculate the values and everything, we are going to get this as 0.1502 e to the power minus t sine of 19.975 t plus 1.0. Okay, okay, this is just x1t. I hope this is clear. But this solution is applicable only for t less than equal to tau. What about when t crosses this tau? So after this, there is a lag in the system, right? Lag as in we can actually portray our system in that form. So what happens is that likewise, when we try to find out the solution in a generalized form for the previous question, we got that x of t was written as f into g of t. Here the impulse was applied at t is equals to 0. Right? The impulse was applied at t is equals to 0. Now what is happening? The impulse is getting applied at t is equals to tau, right? So now what we can do is we can say that for my system, the impulse is applied at tau. It is going to impart the velocity at this point, right? It is going to impart the velocity at this point. Okay. So now if we want to find the solution from this point, we can find it in terms of a new time scale which is defined as t dash. And the relation of t dash is what? T dash is nothing but t minus tau, right? T minus tau. Okay. Because for now, for us, the time t is starting from tau, okay, which is 0. Which is 0. Like for the previous case, we were finding the solution for 0. Now we want to find the solution such that the impulse is applied at tau. So for now, I'm going to what? I'm going to change my time such that it becomes 0 at the point where the impulse is applied. Okay, so then my solution x of t becomes what? F into g of t minus tau. That was what? Time at which impulse is applied. Okay, so now if I want to find out or write the solution, I can write x2 of t as f2 by m omega d into e to the power minus eta omega n. Now instead of t, we are going to write t minus tau. Instead of t, we are going to write t minus tau into sine of omega d t minus tau. So what we have done, we have basically replaced t with t minus tau. We know the value of tau is, I think, not given. Okay, so let's just consider tau as 0.2. Okay, so then this can be written as f2 is 10 by 5 into 19.975 e to the power minus 0.05 20 t minus tau sine of 19.975 t minus tau. Okay, we should put the value of tau over here and here as well. 0.2, 0.2, right? This can be written in the final form as 1.1000125 e to the power minus of t minus 0.2 into sine of 19.975 t minus 0.2. This is x2 of t, which is applicable only and only if an impulse is applied at tau. Okay, but now we have two cases. We have divided our impulse that is applied into two parts. First, we have considered and find the solution for when the impulse is applied at t is equals to 0. And second solution that we found out was when the impulse is applied at tau, right? Now this is fine. Now the thing is that if we have two solutions, we can just sum up these two solutions and get the final solution. However, I would like to mention over here that this is true if and only if our system is working in the linear range. If our system is working in the linear range, then only we can superimpose two solutions and add it to get the final solution. Okay, so using the principle of superposition, the final solution is obtained as x x1 of t plus x2 of t, which is 0.1502 e to the power minus t sine of 19.975 t plus 1.1000125 e to the power minus t minus 0.2 sine of 19.975 t minus 0.2. Okay, so but again we have applied the principle of superposition, and it should be applied only and only if our system is operating in the linear range. So basically the principle of superposition says that, like for example, for an input x, I get a solution y, or x1, I get a solution y1, and for an input x2, I get a solution y2. And the principle of superposition says that if I give an input of x1 plus s2, I'm going to get a response of y1 plus y2. Okay, and this is true for only a linear system. Okay, so principle of superposition applicable only in the linear range, does not apply for nonlinear range. Like for example, if I take, let us say, y as a function of x as x, okay? So, for x1, y1, and for x2, we have y2. And then if I replace x1 by x1 plus x2, it is definitely equal to y1 plus y2. But if I take y as x cube, what do I have? I have y1 as x1 cube, I have y2 as x2 cube, and when I write y1 plus y2, what am I going to get? Okay, sorry. If I take x1 plus x2 whole cube, it is not equal to y1 plus y2. So this is for a nonlinear system, while this is for a linear one. Okay, so the principle of superposition applicable to the linear system. However, for this course, we are working only on the linear range, so it will work, but just keep in mind that this is applicable for the linear range, that this has a limitation of being applied on a system. Now we have question number 3, which says that a compacting machine modeled as a single degree of freedom system is shown in figure. Okay, the force acting on the mass m, where m includes the mass of the piston, the platform, and the material being compacted, due to sudden application of pressure, which can be modeled as a idealized step force, as shown in figure, we have to determine the response. Okay, so essentially, what do we have over here? We have a system which has a mass, right? Which has a mass, and then which has a mass which is connected to the ground by spring and a dashpot. Then there is a spring above the mass, there is a cylinder and piston, and then at the piston there is a force F of t which is applied. Okay, and this F of t can be idealized as a step force, which means it can be considered something like this, which is happening continuously, though it is having a constant value, but it is being applied continuously with respect to time. Okay. And we have to find the solution for the system. Now, first thing is the spring constant. You can see that the spring is in parallel. So the effective spring constant is going to be K. That is clear. Then we have a dashpot which has a damping value of C. And then we have mass M, which considers all the total mass, right? Now we have a force F that is applied. So we have to consider it as a spring mass system. Consider it as a spring mass system. There is a spring, there's a dashpot, and then we have F as F of T. Whose variation? I've shown here. Variation of applied force. Okay, we have to find out the solution. So in the previous case, what we were having? We were having an impact loading, which was happening for a very small amount of time. So we had to calculate the solution, for which what we did was we considered the linear momentum, and then we found out the initial velocity. On the basis of that, we found out the final solution. But the thing was that there the force was acting for some very small time and then it was gone. But here that is not the case. Here a force is acting and it is acting continuously with a constant value. And then we have to find the solution. Now, if it would have been a impact case, we knew how to find a solution. But this is not an impact case. But what we can do is we can essentially divide the force at every time as an impact force. Right? We can divide it as an impact force, and then what we can do is we can just sum up all the solutions. That is what we did in the earlier question. We found out the two solutions corresponding to the two impulse impact, and then we summed up because of this principle of superposition. Similarly, over here, for the total time span, we can divide it into multiple parts. For every multiple part, we consider it as an impact, and for that we find out the solution, and then we can just sum it up. Okay, so if I consider an arbitrary variation of force F with respect to time, let us say something like this. And if I consider a small part over here like this, let us say it is happening at some tau, and this is tau plus delta tau, and this is some F. Okay, and then now we have to find out the solution. So for only for this amount, what is going to be the solution? Only for this amount, I'm going to get delta x of t as F of tau into g of t minus tau into what? Delta t, delta tau. Now over here, like for the earlier two cases, we were having the value of impulse. Here F is the value of the force. Here F is not the value of the impulse, F is the force, and F into delta tau is the impact. So F into delta tau impact into g of t minus tau, which we did earlier. Okay. Now this is for some delta x. Likewise, I have multiple. Okay, so what I can do is for x of t, I can just put a summation on the right hand side. So x of t is nothing but summation f of tau g of t minus tau delta tau. Right? This is going to be the solution. But over here, I'm considering some discrete parts and I'm considering a discrete integration. But what if I want to convert it into a continuous integration? So then I'll change the summation to integral. Further, x of t can be written as integration of 0 to t f of t, or tau to be precise, g of t minus tau d tau, right? This is going to be our total solution. So what we have done is we knew the concept of impulse force, right? If an impulse force is applied, what is going to be the solution? We used that knowledge over here. We actually divided our continuous force into small parts such that it is considered as an impulse. For every impulse, we found out the solution using the equation that we derived for question number 1. After that, we applied a summation for all the range of time. Then we converted summation into integral for continuous integration. Okay. And this form of solution is also known as the convolution, or Duhalm integral. Right. Now g of t minus tau, you remember what is g of t? So we can further write x of t as f of tau into e to the power minus eta omega n t minus tau into sine of omega d minus tau d tau integration from 0 to t. From 0 to t. There should be a m into omega d over here as well. Okay, I hope this is clear. Now, if now I want to use this equation to find out the solution, how will I do it? How will I do it? So see, firstly, if I consider c is equals to 0. If I consider c is equals to 0, what am I going to get? I'm going to get x of t as 1 or f of tau by m. Now omega d will get converted into omega n. Why? Because we have omega d as 1 minus eta square under root into omega n. For c is equals to 0, this is going to be 0. And so omega d is going to be equal to omega n. So we have f of tau m by omega n e to the power minus. So we have e to the power minus eta omega n into t minus tau. Now eta is 0, so e to the power 0 is going to be nothing but 1. I'll write eta e to the power minus eta omega n t minus tau. We have this as 0. This is e to the power 0, which is 1. So this can be written as sine of omega n t minus tau d tau integration from 0 to t. Hope this is clear. Okay. Now, when I integrate this, firstly f of tau is nothing but f. Right over here we have the force as f. And it is not changing with respect to time. F is not changing with respect to time. We have derived the system such that f could be a function of time, but here f is not changing with respect to time. It is treated as a constant. So we are going to write it as f by m omega n integration of 0 to t sine of omega n t minus tau d tau. Okay. So we have the integration of sine theta as nothing but minus cos theta. So because we have the differentiation of cos theta as minus sine theta, so integration of sine theta leads to minus of cos theta. So now we have the integration as f by m omega n square. Omega n square because if we have any integration of the form let us say integration of f of ax dx. We are going to get the value as, let us say the integration of f of ax with respect to dx is g of x. We have a by a. That is why we are going to have a omega n square in the denominator. Then we have minus of cos omega n t minus tau, and the limits of integration goes from 0 to t. Okay. Now, when we put the limit of integration, we get f by m omega n square into minus of cos 0, and then we have minus minus plus cos of omega n t. So we finally get the value as, no, it should be upper value. Okay. Omega nt, and here it should be 0. So we have f by m omega n square 1 minus cos of omega nt. Further, we also have omega n square as k by m. So if I put the value of omega n square in the denominator, m will get cancelled, and the final equation becomes f by k 1 minus cos of omega nt. So this is going to be our solution. I hope this is clear. It was very simple. Just a simple integration. Now, further, if I consider the damping, what is going to happen? So for damped system, what do we have? We have x of t as, we had f of tau m omega d e to the power minus eta omega n t minus tau sine of omega d t minus tau d tau integration from 0 to t. Right? We had this form. Now again, f of tau is actually constant with respect to time, so we can take it out of the integration, and omega d we can write in terms of omega n and eta, so we get it as f by m omega n under root of 1 minus eta square into integration from 0 to t e to the power minus eta omega n t minus tau into sine of omega n under root of 1 minus eta square t minus tau d tau. And we can just close the bracket. So this is the integration that we have to perform. So we basically have two functions that we have to integrate with respect to tau. So by the rule of integration, we can basically find it by using 1 minus eta square into. So we have first function into integration of second function minus differentiation of first function into integration of second function d tau and this whole needs to be integrated with respect to theta. Then we have to put the limits of integration from 0 to t. So when you do all this integration, which I'm skipping for now because this is simple integration, we don't need to waste time on this. We get the final answer as f naught by k into 1 minus 1 by under root of 1 minus eta square e to the power minus eta omega n t into cos of omega d t minus phi, wherein you'll get the value of phi as tan inverse of eta by under root of 1 minus eta square. Okay, so this is the solution if a constant force of magnitude F is applied to a spring mass dashpot system with respect to time. Okay, so this is solution for a spring mass dashpot system subjected to a constant force F. Okay, I hope this is clear now. Now coming on to question number 4, which is somewhat related to what we have done in question number 3. The only difference is that in the earlier case, we had a constant force F which started at time t is equals to 0, but in this case, this force F is shifted to t naught. Everything else is the same. The only difference is that now the force F is acting at a time t naught. Okay. So what are the changes that are going to happen? The change is going to be nothing but, if you remember for the previous case, what we were doing, we were replacing the time, right? So here also what we are going to do is that we are going to just change the limits of integration to find out the solution. Okay. So now we are going to write x of t as integration f by m omega n under root of 1 minus eta square e to the power minus eta omega n t minus tau into sine of 1 minus eta square omega n t minus tau d tau from t naught to t. Okay, so from t naught to t. So when you'll do all the calculation and everything, you're going to get the final solution as nothing but f by k 1 minus e to the power minus eta omega n t minus t naught divided by under root of 1 minus eta square into sine of okay, should it be cos omega d t minus t naught minus phi. The phi is going to have the same value as in the previous question. The only difference is that now t is being replaced by t minus t naught. We are going to get it from the integration, and you can check it after doing the integration of your own. Okay. Let me just check over here. Okay, that's fine. Okay. Again, if you want to try it for a undamped system, for the undamped case, we are going to get x of t as integration from t naught to t. We have f naught by m omega n, and then we have sine of omega n t minus tau d tau, right? So we are going to get f naught by m omega n minus of cos, here it will be omega n square cos t minus tau omega n, and the limit of integration will be from t naught to t, from t naught to t. So this time when we put the limits of integration, we get f naught by m omega n cos of omega n t minus t naught plus, here it will be minus, cos of omega n t minus t. So this will give us f naught by m omega n 1 minus cos of omega n t minus t naught. You can derive this from the main equation that we got earlier, like from this equation. If you put eta 0, then you can derive the same expression like over here. So what you can notice from over here is that again we can also change one thing. We can write this as k. So if we compare for the system where a constant force was applied at t is equals to 0 and when a constant force was applied at t is equals to t naught, there is only a difference that the terms which were in terms of t are now replaced by the terms which were in terms of t minus t naught. Okay, so you can remember this also for in order to attempt any question. You don't need to go through the derivation again. If you remember one approach, you can just substitute t minus t naught in place of t and then find the solution. So now when you have this equation, if I tell you that okay, for a system, these are the mass, damping and stiffness values, and then a force, let us say 20 Newton is applied at a time of 5 seconds, then what is going to be the response of the system at time is equals to 10 seconds. So you can just using this equation put all the values in the equation and then substitute the value of t as 10 and t naught as 5 and get the solution. Okay. Now coming on to question number 5. So this was it about all the impulse response related questions, and I hope from this you will get the value, get the solutions of the questions that are given in the assignment. Like previous week also we solved some question related to the impact loading, but it was for the case when we were actually trying to find out the equation, solution equation, or when we were trying to find out the amplitude value, nothing else, right? So we were just using the value of the force and how much time it is being applied in order to find out the amplitude of the oscillation which is going to happen after the impulse is applied. But over here we attempted 4 questions wherein we actually considered a spring mass dashpot system and we tried to derive the solution, the closed form solution, in terms of time and all the parameter values, such that we when we apply a impulse, if we apply 2 impulses which have a small span in between them before in the between the application, and when we have a constant force that is being applied to the system, and when this constant force instead of starting at t is equals to 0, it starts at after a certain amount of time, right? So we have derived the solution in terms of closed form equation and then which we can use in order to get the final solution. Okay. Like, this type of impact loading related solution that we are finding is actually helpful for us in order to find out some properties of the system. Like, for example, if I have a system that has some mass and it has some stiffness, and I don't know what is going to be the damping value. So what I can do is I can do the impact testing. I'm going to get the response of the system with that impact testing, and from that response what I can do is I can find out the value of eta. Like I know the equation form. Okay, I know the equation form. I have the value of mass, I have the value of stiffness, and I know that at t is equals to 0 what is the displacement, at t is equals to 10 second after applying the impact what is the displacement of my system. So I can just put it in that equation along with the impact force and I can find out the value of eta, from which I can estimate what is going to be the damping value of the particular system. Okay, but then again this is applicable only for the linear range of the system. Okay, it is applicable only for the linear range. If we are considering a system where the deformation is more than 3% or 4%, for that we have to now consider the nonlinear equations. This is applicable for a system where the deformation is around 3% or 4% of the length of the system, or whatever the dimension in which the deformation is happening. Okay, so now when we come to question number 5, we have a spring mass system that has a mass of 10 kg, a damping value of 20 Newton second per meter, stiffness as 4000 Newton per meter, and initial condition with initial position as 0.01 meter and velocity 0. Then find the total response of the system for free vibration when a harmonic force act on when a harmonic force act on it. So we have essentially a spring, a dashpot, and then there is a mass m. Okay, and the initial velocity is 0, but initial position is 0.01 meter. We have mass as 10 kg, C as 20 Newton second per meter, and K as okay. So we have to find the response of the system for free vibration and when a harmonic force acts on it. Okay. Considering the first case, which is the case for the free vibration. Okay. Firstly, we'll try to find out all the non-dimensional forms of a system. So omega n is under root of k by m, which is 4000 by 10, 20. Then we have eta as c by cc. Cc is the critical damping constant, 20 by twice of under root m, and k. This is given as we have 40,000, so 20 1 by 2, 0.05. Okay, then we have omega d, omega n under root of 1 minus eta square. This will be around 19.975 radians per second. Then we have R, which is the ratio of omega by omega n, and this is given as yeah, this is omega by omega n. So, for example, let us consider F as forcing function of the form x, not x, f cap cos omega t. So we are going to have 100 cos of 10t. Let us consider f as this for now. So we'll have r as 10 by 20, which is 0.5. Okay, for finding the solution for a damped system and harmonic excitation, we need to find delta st, which is the static deflection, which is given by nothing but f by k. So 100 divided by 4000. This will give 0.025 meter. Okay, and what else? Eta we have found out, omega n is done, omega d is done, r is done, delta st is done. Okay, these are the things that we find out that we would want. Okay, now when we have to find out the solution, right? Yeah. Now for the harmonic excitation, if there is some kind of a harmonic excitation in the system, how do we write the solution? How do we write the solution? So solution is written in terms of Sx cos omega t minus phi, x cos omega t minus phi, right? Where x is nothing but delta st divided by under root of 1 minus r square whole square plus 2 eta r whole square, right? 2 eta r whole square. And phi is nothing but tan inverse of 2 eta r divided by 1 minus r square. Okay. Now, if I evaluate these two values, because I already have the values, right? I can just evaluate it. X will be delta st, which is 0.025 divided by under root of 1 minus r was 0.5 whole square plus 2 eta 0.05 into 0.5 whole square, right? So this turns out to be, let me just check what is the exact value that we get. 0.03326 meters. Okay, this is the value of x that we are going to get, and for phi we are going to get tan inverse of 2 0.05 into 0.5 divided by 1 minus 0.5 square, right? So for this we are going to get 3.81407 degrees. Okay, I've done all the calculation, you can recheck it. Now, when we talk about the solution x of t, see, it is important to understand that for a system which is having a damping present, and when it has a certain initial condition, it is first going to show some transient vibration. At the end, since it is having a forcing function, it is going to have a response which will have the frequency which will be equal to the frequency of the forcing function. But that is for the case when we consider the steady state response. What if we want to find out the whole response? Now in the question, there is nothing specified as in whether we have to find out the steady state solution, the transient solution, or the total solution. So until and unless it is not specified that we have to work on the steady state solution, we are going to find out the whole solution, which is going to be applicable for both the transient phase and the steady state phase. So x of t can be divided into two parts, right? One is because of the periodic response which will happen in the steady state, which can be written as x of pt, right? And the second one is going to be what? The transient response, that can be written as x of ht. This is because of the transient and this is because of the steady state. Now we know that we are working in the linear range of the system and hence the principle of superposition is applicable. So this is absolutely true. Okay, but if would have been working in a nonlinear range, we cannot write by adding x of pt plus x of ht. Now for the steady state response, I already have the values. For the steady state response, the solution is nothing but x cos of omega dt minus phi. Yeah, here it should be omega d, which is the damped natural frequency. X cos of omega dt minus phi. We have evaluated the value of x as 0.03326 meters, and then we have the value of phi as 3.81407 degrees. Okay, so we can just put in those values. But what about transient state? So transient state can be written as, let us say, x cos omega t minus phi. Okay, firstly, we cannot write it like this because we need to differentiate x and x naught. So we can just write it as x naught. For the steady state, we'll write x naught. Then we have e to the power minus eta omega nt cos of omega dt minus phi naught. Okay, fine. Now, since we already have these values, we can just put it, right? We can just put it. So we are going to get for x naught, what do we have? We have now see over here, what we have done is we have actually divided xt as what? As what is going to be the, because of transient, and this is the steady state. I have written opposite. This is the steady state, and this is the transient. So for the steady state, we already have the values. So we can just write, now we are assuming, like we are trying to find out for x naught. Now for x naught, the time is what? Time is 0, right? And then we have cos of minus of phi naught. So cos of minus theta is nothing but cos theta. So we are going to have x naught cos of phi naught plus capital X. We already have 0.03326 into, we have omega t minus phi. Phi we have as 3.81407 degrees. So cos of 3.81407 is nothing but, it comes out as, okay, I've not written the value, but it will come out as a value. So you can write like this. I've written the value of x naught cos of phi naught as minus 0.023186. Okay, this is what you are going to get. And then x naught is given as 0.0. It is already given in the question, 0.01. Right? This was already given in the question as 0.01. So if you'll put this, you are going to get x naught cos of phi naught as this. Okay. Another thing is that since we have the equation of x, we are going to have an equation of x naught as well, right? And this x naught dot is nothing but 0 as it is specified in the question itself. So we are going to write x naught dot, which is equals to 0, is given as eta minus eta omega n x naught cos of phi naught plus omega d x naught sine of phi naught plus omega sine phi plus omega into x omega sine phi, x omega sine phi. Now when I put the values over here, I have the value of x naught into cos phi naught, and then x naught dot is 0, eta I have as 0.05, omega d is 19.975, x naught we have to find out. So x naught sine phi naught, we'll let it be. X we have at 0.033, omega we have 20, and phi we have 3 point something degrees. So when we'll put these values, we are going to get the equation as minus 0.05 into 20 into x naught cos phi naught we have obtained over here minus 0.023186 minus 0.023186 plus 19.975 x naught sine phi naught plus x is 0.03326 into 10. Omega is 10 because it is the forcing frequency, right? Then we have sine phi as sine of 3.81407 degrees. Okay, so after calculating everything, we are going to get the value of x naught sine phi naught as minus 0.002268. Okay, so now since I have sine phi naught and cos phi naught, what I can do is I can just divide these. I can write x naught sine phi naught by x naught cos phi naught as tan phi naught, which is equals to 0.002268 divided by 0.023186. This will give me the value of 0.09781776, and phi naught will turn out to be 5.586765 degree. This is the value of phi naught. So the last thing that I have to find out is the value of x naught, right? So we can use any of this equation, like for example, if we use this equation, we are going to get the value of x naught as 0 minus 0.002268 divided by tan of 5.586765. So this is going to get the value of x naught. Now we have the value of x naught, we have the value of x, we have the value of phi, we have the value of phi naught. So we can finally get the solution in what form? In this form. Over here, like this, we can write the solution. xp plus xh, like the final solution I can get as there was x naught, which I have to x naught x naught e to the power minus 0.05 into 20. Okay, this I can write as directly t, then cos of omega d into t, cos of 19.975 t minus phi naught 5.586765. This is in degrees, but we need to change it in radian. Okay, we need to change it in a radian. So what we can do is we can just do it into pi by 180. Okay, we have plus x, which is 0.03326 cos of omega 10t minus phi, which is 3.814075 into pi by 180. So this is going to be the final solution. Okay. Now the second part was we had to find out the response for free vibration and with harmonic force. So we have already found out the value, the solution for when the harmonic force is acting, but now we have to find out the solution when a no force is acting. Okay, so we have just given some initial condition to the system and we need to find out that how the system is going to respond. Okay, so when no harmonic force is acting. What do we write? We can write the solution simply as x of t is equals to x naught e to the power minus eta omega n t cos of omega d t minus phi naught. There's no going to be a steady state component. Everything is going to turn out from this only. Okay. If no force is acting, it is going to stabilize to an equilibrium state. In the previous case, a harmonic force was acting, because of which the system is going to show some sort of a periodic oscillation in the steady state. So we summed up the transient plus the steady state, but here in this case it is only going to be the transient, and in the steady state it is going to occupy some equilibrium position, whichever is its equilibrium position. Okay, now for this system the equilibrium position is definitely 0 0, velocity 0 and position 0. Okay, so we have x naught as 0.01 and x naught dot as 0. So here x naught and phi naught can be written as what? So x naught is x naught square plus eta omega n x naught divided by omega d square, and this whole has a power of 1 by 2. So when we put these values, we get 0.01 square plus 0.05 into 20 into 0.01 divided by 19.975 whole square to the power 1 by 2. Okay, so when we put all these values, what do we get? 0.010012. Okay, now when we find out the phase angle, it is nothing but phi naught as tan inverse of minus of x naught dot plus eta omega n x naught divided by omega d x naught. This can be written as tan inverse of minus 0.05 into 20 by 19.975. So we get it as minus 2.865984 degrees. Okay, I hope this is clear. This was easy, and this was already, you can find it in the book also, that how do we get these relation of x and phi. It is given in the book. I'm not getting into derivation of this. This is basically found out by, you have the equation in this form, this. Yeah, you have the equation in this form. So what do? You equate this is going to be equal to x naught for time t is equals to 0. Then you're going to differentiate it, and then you are going to equate the equation for time t is equals to 0, and which will be equal to x naught dot. And then from those two equations, you are going to do some of the mathematical manipulations in order to get the final equation of x naught and phi naught. And then you're going to just put these values in these two equations, and you're going to get the answer. So coming on to question number 6, which is about an eccentric weight exciter. So eccentric weight exciter is used to produce the forced oscillation of a spring mass system. Okay, and amplitude of 0.6 centimeter was recorded at resonant frequency, and the amplitude of Yeah, so an amplitude of 0.6 centimeter was recorded at the resonant frequency, and an amplitude approaches a fixed value of 0.08 centimeter for frequency considerably beyond the resonant frequency. So we need to find out the damping factor of the system. So first thing is, there is an eccentric weight exciter. Okay, so there's nothing more difference. See, this system, there is only this one term eccentric weight exciter that is changing the perception of this problem. Okay, this problem is very simple, but this thing is just making it complicated. So firstly, we understand that for a spring mass dashpot system, which is of the form mx double dot plus cx dot plus kx is equals to f sine omega t. Okay, we have something which is called as the capital X magnification factor. Okay, we have the magnification factor which is written as capital X divided by delta st. X is what? X is the amplitude of the oscillation of the system. Delta st is what? Delta st is a static deflection of the system if a force F acts on it. Okay, and this magnification factor is written as 1 by 1 minus r square whole square plus 2 eta r whole square under root. R is what? Omega by omega n. This is natural frequency. This is the natural frequency. And omega is what? The forcing frequency. Eta, damping ratio. Eta is the damping ratio. Okay. Now, this was easy for a spring mass system with a forcing F sine omega t. But now we have a eccentric weight exciter, right? So what is the difference that we are facing over here? See, the delta St was actually defined as F by K. Clear? Now, this is the form which is written in terms of R and eta. What if I write it in terms of M and K? Then X is going to be F by K minus M omega square whole square plus C omega whole square with a under root. Okay, something of this type. Now, the first thing is that for an eccentric weight exciter, how is this F actually defined? So, for an eccentric exciter, it is something like you have a circular disc. So, you have a circular disc, and this is its center. Now, if it rotates, it is not going to experience any kind of vibration, provided the mass is distributed homogeneously and evenly. Now, if the mass is not distributed homogeneously, at some point the mass is more, at some point the mass is less. Now, because of that, it is going to have some kind of a residual vibration when it is rotating. So, to model that, what do? We take this disc and then we mount it over here instead of center at some eccentricity with respect to the center. So this is the center and then we mount it from here. And this is E. This E is the eccentricity, E. Okay. Now because of this, if the system is rotating with respect to this blue dot, what is going to happen? More weight is over here than over here. So it is going to create some residual force when it is rotating. And that residual force is going to cause oscillations to the system. The thing is that how do we now write this? The mass, let us say that here is some mass, and then we are going to have some force. We know m omega square r we are going to have as a force, which is defined as the centrifugal force for a system which is rotating. For here, it is having some other mass. The difference between these two masses is small m. In that case, the residual force is what? M omega square E, where E is the eccentricity. Okay, and this point is actually changing. It is actually changing its place with respect to time, corresponding to the frequency omega. So I can now write F as M omega square E. Minded, this M, I should change it. This M is different from the mass of the spring mass system. Okay, so essentially we have a system like we have a mass, there's a spring, there's a dashpot, and then there is this rotor which is mounted over here. Now this rotor is rotating, because of it is causing a movement of mass m, and the residual mass m is concerned with the rotor, and because of that the oscillation or the forcing that is happening, it is of the form m omega square E into sine of omega t. Okay, so now the x can be written as, in terms of m omega and E, as m E omega square divided by k minus m omega square whole square plus c omega square. Now what I can do is I can write this like m by m, this should be replaced by capital M over here also, this should be capital M. Okay, somewhat like this. Now I can write this as capital M by small m into x by E is equals to omega by omega n square divided by 1 minus omega by omega n square whole square plus 2 eta omega by omega n square under root. Okay, now this is the expression that we are going to use. Now in the first case, it is written that in the first case we have that an amplitude of 0.6 centimeter was recorded at resonant frequency. So at resonant frequency, this R, which is omega by omega n, is 1. So we get mx by me is equals to 1 by 2 eta, which is equals to 0.6 centimeter, or we can write it as 0.6 by 100. Okay, 0.6 by 100. Or maybe we can just write it as 0.6, or just let it be in meters. Okay, so this is the first equation. For the second case, we have the amplitude approaches a fixed value of 0.08 centimeter for frequency considerably beyond the resonant frequency. For a frequency considerably beyond the resonant frequency. Now, when we say that the frequency is considerably beyond the natural frequency, what do we say? What do we have? We have omega is very, very greater than omega n. Omega is very, very greater than omega n. Okay. So in that case, what is going to happen? In that case, in the denominator, the dominant part is going to be what? Omega by omega n square. Right? That is going to be the dominant part. Firstly, eta is what? Eta is very small. Okay. So we can just neglect that part. But for 1 minus omega by omega n square, we have omega by omega n, which is a very large value, and then we have its square, right? And then we have 1 which is deducted from which it is deducted, so it does not cause any much change in the value, okay? Like multiplying a number, a very big number with a small value, it's going to change its effect to a smaller value. But subtracting 1 from a very big value, is not going to cause any big change into the system, okay? So in the denominator, we are going to get effectively the value of omega by omega n square, and both will get cancelled from the denominator and numerator. So at the end, we are going to get mx by me equal to 0.08 divided by 100, right? Now we are supposed to find out the value of eta in the problem, okay? So what we can do is we can directly substitute the value over here, right? We can directly substitute the value. Not here actually. The value should be substituted. Firstly, this shouldn't be written in this form. It should be m e by m, right? Here also it should be m e by capital M. So we can just substitute this over here. So what are we going to get? So we have 0.08 divided by 100 into 2 eta is equals to 0.6 divided by 100. 100 would get cancelled, and eta is effectively going to come out as 0.08 divided by 0.12, and this finally gets a value of 0.0666. So eta is 0. So this is the final answer to this question. I hope this is clear. Coming on to question number 7. So question number 7 says that for a weight of 50 Newton, a weight of 50 Newton is suspended from a spring of stiffness 4000 Newton per meter and is subjected to a harmonic excitation of amplitude 60 Newton and frequency 6 Hertz. Find the spring extension because of the weight, the static displacement for maximum applied force, and the amplitude of forced motion. Okay, so this case is something like we have a fixed support, we have a spring, we have a dashpot, we have a mass. We have mass as 50 by 9.81 because the mass is given in terms of its weight. So its mass can be found out by dividing it with the gravitational acceleration. We have K as 4000 Newton per meter and C as, okay, we don't have a dashpot over here. That's nice. The question becomes easy then. We don't have a dashpot, we just have a mass. Yeah. And another thing is that we have a harmonic excitation of the type 60 sine of 6 Hertz 2 pi 6t. 2 pi 6t. So firstly, we have to find out the spring extension because of the weight, which is simple because in that case, we are going to have the mass with weight and K delta. So 4000 delta is going to be equal to 50. So delta is going to be 50 by 4000 This will come out to be 0.0125 meter. Okay, after that we have to find out the static displacement for maximum applied force. Okay, so by maximum applied force, what does it mean? See, the F is actually of something like a sine of omega t. Sine of 0 is going to be 0. So we have a maximum value. Then a minimum value, then a maximum value, then a minimum value, something like this. This is F time. So it's saying that for a maximum value. But what do we know? We know that this is equal to what? F naught. If F is given in the form F naught sine of omega t, this is F naught and this is minus of F naught. Right? So when it is asking for the static displacement for maximum applied force, it means that what is going to be the displacement, static displacement, if F naught is applied on the system. Okay, and we know the value of F naught as 60. F naught is 60. So in that case, this for 1, for 2, we have K X, it should be K delta ST as 60. So delta ST is going to be 60 by K or 60 by 4000, and this will give a value of 0.015 meter. Okay, this is going to be delta static. Third, we have to find out the amplitude of forced motion. So we had an expression of the form capital X by delta static is going to be nothing but 1 by 1 minus r square whole square plus 2 eta r whole square under root. Right? We have the value of delta static as 0.015 meter. Okay. And we need to find out the value of r. Eta we already know is equal to 0. Eta is already equal to 0, so we need to find out the value of r, which is omega by omega n. Omega n, which is the natural frequency of the system, is under root k by m, which is under root of 4000 divided by 50 into 9.81. This will give the final value of 28.0143 radian per second. Okay, and then we have omega as 2 pi into 6, which is 37.6992 radians per second. Okay, so now if we put these values in that equation, we're going to get x by 0.015 is equals to 1 divided by this square and under root are going to get cancelled. This will go to 0. So we have 1 minus 37.6992 divided by 128.0143 whole square, this whole square, and under root will give the value of 0. Okay, I have the final value actually. So in the middle calculation, you can do it on your own. It's going to give us a value of 0.0185 meter. So x, which is the response amplitude, has a value of 0.0185 meters. Okay, coming on to question number 8. For a spring mass system placed on a plane inclined at angle theta, find the solution when it is subjected to a harmonic forcing. So earlier case we had a, just a second. Okay, so we have a spring mass system, but the thing is that now it is inclined at an angle of theta. Okay, so the system is somewhat like this. Earlier, what we were studying, or we have studied in the book or in the lecture, we had a spring attached to a mass m like this. But now the difference is that this incline, this reference of ours is now inclined with respect to the horizontal like this. This is some angle theta. Now we have to find out the solution when it is subjected to harmonic forcing. Let us say like this, F sine omega t. Then what is going to be the solution of the system? So firstly, finding out that how the system is going to behave on an incline. If I make its free body diagram at some point, it is going to be mass m is going to experience a weight something like this, mg. And we know the angle theta, so this mg can be broken down into two parts, right? By geometry, you know that this is going to be the angle theta. So this is going to be mg cos theta, mg sin theta. There's going to be a spring force K into x plus delta. So x is essentially the, let us say, movement after it has reached the equilibrium point, and delta is the equilibrium stretch of the system. See, if I have a mass which is inclined like this, and if I don't apply any forcing, it is going to attain an equilibrium point. Once it has attained that equilibrium point, and then I apply this forcing, okay, so the force will constitute both the x and delta. Okay, so these are the forces, and then we have x defined like this. So now if I write the equation of motion, how is it going to be? Okay, it is going to be m x double dot plus k x plus delta minus mg sine theta is equals to f naught sine of omega t. Okay, f naught, or maybe we can write it as cos also, cos of omega t. So this is going to be the equation of motion. Correct. Now we already know that k of delta is going to be equal to mg sine theta because it is the equilibrium state. So this will get cancelled and the final equation comes out to be nothing but mx double dot plus kx is equals to f naught cos of omega t. So what do we see over here? Though our system has changed, the reference or the plane on which the mass was kept, it is now inclined at an angle theta. But the equation, final equation is still the same in terms of x. In the mathematical form, it is same. However, in the previous case, the x was defined parallel to the horizontal. Here, the x is defined at an angle theta from the horizontal. But the final form of the equation is exactly same mathematically. So, but physically, definitely, it is different. So now, if I want to find out the solution for this, I already know it, right? I already know the solution. The steady state solution is going to be nothing but x cos of omega t minus phi. X cos of omega t minus phi, where where x is nothing but f naught by k divided by 1 minus omega by omega n square, and phi is 0. So this is going to be the solution of the system when it is subjected to forcing. Then coming on to question number 9, which says that obtain the frequency ratio for which the maximum amplitude is attained by a spring mass system and its value. Find its value. Okay, so basically this question says that we need to find out the frequency ratio at which the maximum amplitude is attained by a spring mass system, and then we also need to find out that what is that value. What is that particular value? So firstly, we have x as delta st divided by under root of 1 minus r square whole square plus 2 eta r whole square. In order to find out the maximum value of something with respect to a variable, what do? We differentiate it. So we differentiate t of x with respect to what? T of r, and we get delta st. We have minus 1 by 2, so minus by 2. In the denominator, we have 1 minus r square plus 2 eta r to the power 3 by 2. And then in the numerator, we are going to have twice of, it should be r square, 1 minus r square into minus 2r plus twice of 2 eta r into 2 eta, and this should be equal to 0. This whole term we can take here and make it 0. So we are going to have 2 also we can cancel out with this. So we are going to get minus 2r plus 2r cube plus 4 eta square r is equals to 0. This can be written as r into 1 minus r square minus 2r. 2 eta square is equals to 0. Now r cannot be equal to 0. So 1 minus r square minus 2 eta square is equals to 0. Okay. So this implies r square is equals to 1 minus 2 eta square, or r is equals to under root of 1 minus 2 eta square is the value of frequency ratio, at which maximum amplitude is attained by the system. Okay. And we also have to write out that what is actually the amplitude. So again, if we put, so x at r is equals to under root of 1 minus 2 eta square, we have delta st divided by under root of 1 minus r square minus 1 plus 2 eta whole square plus 2 eta under root of 1 minus 2 eta square whole square. So this turns out to be delta st divided by under root of 4 eta square plus 4 eta square minus, we have 4, 4 to the 8 eta cube, which is delta st divided by under root of 8 eta square minus 8 eta cube, which will be delta st divided by 2 under root 2 eta into 1 minus eta square, and this is going to be the maximum value. Okay, coming on to the last question, and we'll complete in time only. So the last question says that obtain the, okay, find the damping ratio for a spring mass damper system when an amplitude of 20 mm is obtained at the resonance and 10 mm at frequency 0.75 times the resonant frequency. So we need to find out the damping ratio, and the information that is given in the question is that we know the amplitude of a system when the frequency is equal to the resonant frequency and when the system is equal to the 0.75 times of the resonant frequency. So if you look over here, again we have the relation x is equals to delta st divided by under root of 1 minus r square whole square plus 2 eta r whole square, such that r is omega by omega n, and yeah, eta is what we have to find out, so no need to write elaboratively what is eta. So for the first case, r is equals to 1, since the frequency is equals to omega by omega n, we have x is equals to delta st by 2 eta, and the value is given as 20 mm. 20 mm, which is 20 divided by 1000. For the second case, we have r is equals to 0.75. So we have x is equals to delta st divided by 1 minus 0.75 whole square plus 2 eta 0.75 whole square. Okay. Now, if you look over here, what we can do is we can just find the value of eta in terms of delta st, which will come out as 1000 divided by 40, 0 gone, 4 0.0. Okay, we can write delta ST as 0.04 eta. Okay, so what do we have? This value we have as 10 mm. This is 10 divided by this. Now when we solve it, what do we get? We get 0.01 divided by 0.04 eta. 0.01 was the value, and then delta ST was obtained as 0.04 eta. This was equal to 1 by under root of 0.1914 plus 2.25 eta square. So if we are doing squaring on both sides, what are we going to get? We are going to get 16 eta square is equals to 0.1914 plus 2.25 eta square. Right? So when we take it over here, 16 minus 2.25, eta square is going to be 0.1914. Eta will be nothing but 0.1180. This is the value of the damping constant. Okay. So I hope it is clear to every one of you, and every problem was simple and understandable. However, if you have any doubt, you can ask. Okay, I think there is no doubt. So we'll end this live session over here, and we'll meet next week for the next week live session. And I hope that you people are actually practicing the questions. If you have any doubt, you can ask in the next live session. Okay, so thank you so much for joining. We'll meet next week.